since you did teach gift sampling last semester, can I tell you what I think it is, and you tell me how wrong I am?
Yeah.
Okay, scale 1 to 10. It's an MC method.
Yeah.
You the Monte Carlo part of it is you generate a random sort of idea of what should be possibly in this distribution.
Yeah.
And then the Markov chain part of it tells you if you should accept or reject it based off the assumptions of what should occur in your distribution.
There is no accept reject in this version. I mean, gift sampling. There's accept reject in Metropolis Hastings versions. So we'll discuss. I mean, when we recollect, you will be able to cement, what exactly is gift sampling. Okay. So let's do that actually. So what we're moving towards is again the same problem. Okay, we're not doing any learning. So all the parameters of the joint distribution are already known. What we want to do is inference. Okay, and we're going to do inference using sampling techniques. In particular, we're going to look at Markov chain Monte Carlo. Okay. Sorry. So here, I mean, I just posted this link on the forum. Okay, so there's actually a good. So there are many different sampling techniques. Okay, so you can see there are so many references here. No U-turn sampler is very popular. Hamiltonian Monte Carlo is very popular. But what we're going to look at is Gibbs sampling. Okay, so all I'm trying to say in this page is that Gibbs sampling is one technique, and we will actually see the animation very soon. But before that, let's start with some warm up. Okay, which is. We're going to do but before the warm-up itself, what's the goal? The goal is to do inference, but now it's going to be approximate because we're going to sample. We're going to sample as in we're going to use actually realizations from the joint distribution. Okay, and we're going to sample, and we're going to still answer the same question: can we compute the marginals? Can we compute the expectations? Or can we compute conditional probabilities and stuff like that? Okay, and so there are many methods. So I just broke it into two parts: the warm-up part and the Markov chain Monte Carlo part. The warm-up part is just things like importance sampling and rejection sampling, which are just simple ideas. Okay, and actual part, which is this is what we care about: Gibbs sampling. And there's also Gibbs sampling and Metropolis Hastings. There's another algorithm which involves accept reject. Okay, so these guys are part of this MC method family of methods to do sampling. Okay, to sample. So what do we care about? So what are we doing here? We want to do inference. Okay, let's say we want to compute expectation of x. Okay, over some distribution. That's an inference problem. Okay, the distribution is known, nothing to learn. You just want to find expectation. Sampling just says, oh, why don't you do this expectation with some estimate like 1 by n sum over xi, I is equal to 1 to n. Okay, that's roughly what it is. Sampling just means that, oh, I want to find an expectation. This is some integration or summation operation, right? Instead of that, as long as I can get some samples from this distribution B, I can just average it out. I can just take the average of the samples. Okay, that's roughly the core idea. It's all about dealing with samples to estimate. Okay, let's call it little x to be consistent. Just get some samples, little x size, and then do some computation based on little x size. Okay, drawing histograms or taking expectations like this and so on. So let's start with the first warm-up idea, Monte Carlo averaging. It just means what I just said. If you want to find expectation of f, you would ideally do an integration or an averaging or a summation like this. Instead of that, it says, okay, just draw L independent samples, x1, little x1 to little xl, from the distribution you care about, this P, and then just average them. Okay, if you take L samples, you get x superscript L. Just average these samples. If you want to get an expectation with respect to f, take the f on these samples, average them. That's your estimate for the expectation. Okay, that's the estimate. So expectation of f hat. Sorry, not this one. Sorry, this is the estimate. Okay, you get L samples from the distribution you care about. Take an average. Okay, that's an approximation for this guy. Okay, why is this? So this bottom part is a statement about, because I'm getting samples, expectation of f hat is an estimate, right? It's a function of a bunch of random variables. Its expectation is the same as the true expectation that you care about. This is a analysis fact. Don't worry about it. This is the computation thing. If you get L samples from the distribution that you care about, just average them. That's an estimate of your expectation. Okay. As long as you have this way to sample. Okay. So that's the powerful part.
Is there any feedback here that lets you know if you're sampling right from like?
No, you just need to get samples from the target distribution. As long as you're doing this correctly, then this estimate is supposed to be, in fact, by law of large numbers, this estimate is going to be equal to expectation of f. Okay. There are different statements of law of large numbers, but just intuitively, this f hat is going to be very close to expectation of f, as long as you get samples from p. Okay, independent samples from p. So getting the samples from p, you may be doing some mistake. Then that's a bug in your routine, right? Okay, so what I'll do is actually skip importance sampling and rejection sampling, because it's basically importance sampling is a variance reduction technique. So for doing the same type of averaging, so averaging that we already saw, this was the core idea, and importance sampling is just improving on it. So we'll skip that. And rejection sampling is slightly different. It is actually doing an accept reject stuff. So maybe we'll look at rejection sampling, okay, for a couple of minutes. So what is rejection sampling? I want to get samples from P of X. So what is the problem for rejection sampling? I want to get samples, right? XL from P, right? The first slide said get samples from P. But the problem is you may not be able to always get samples from P, okay? So in that case, what you do is, so maybe the P distribution looks like this, okay? This red probability density function, okay? But you can't directly sample from P. Let's say you don't have a function called to sample from P, but you have a function which can sample from Q. Okay, so let's say Q is a Gaussian distribution. Then looks very symmetric and nice. Okay, maybe you have a np.random.random or something that from where you can sample. So the question is, how do I use that guy to get samples from this? From the distribution that I care about, like P or P tilde in this case. Okay, so the way you do it is get a number k. Okay, such that the probability density function of k times Q supersedes the density function of this red curve. Okay, so that's the first step. You can pick up a large multiplier. K can be like 10 or 100 or something, so that the whole this red curve is below the blue curve. Okay, and that's it. That's step one. And step two is now samples. Okay, the way you do it is sample from Q. Okay, you get some number. That's a z0. Okay, now you sample. So at z0 you can evaluate q. What is k times q of z0? Because you can just figure out the density function. You have the CDF you have the density value PDF for the normal distribution. You can plug in the z that sample that you got to know what the value of that PDF is at that point, right? So this number. Okay. Now what you do is you can sample a uniform random variable between 0 and this number. Okay, this is some number. Let's say it's 10. Okay. So between 0 and 10, draw a uniform random variable. Okay. Now you check whether the uniform random variable is taking a value below P, below P of Z0 or above P of Z0. Okay.
How do you know that if you don't know?
So you can evaluate P of Z0, but you can't sample from P of Z0. So the problem is you have this function P of Z0. If you plug in Z0, it will tell you what's the probability of something, probability of Z0, but you cannot get a sample from it, okay, because it looks very messy. Maybe it's like a very messy function where you don't know how to sample from this probability density function, but you can evaluate for a given Z0 what the value is. Okay. So the sampling is happening in two steps. First, you just generate a sample from this blue thing. Okay. Once you got the sample, look at the line from 0 to kq of z0. Draw a uniform random variable that can fall on this side or this side. Okay. If it falls on this side, you reject the sample. If it falls on this side, you accept the sample. Okay, and that's it. And then you go to the next step, which is again draw a sample. Maybe here now z0 is over here. Draw a uniform distribution. Draw a uniform sample. Maybe in this case, and you can see that the whole line is under red, so you will probably accept it, and so on. Okay? So that's how you do rejection sampling. Okay. The whole point is you don't have access to sampling from P, but you can evaluate P, and that's it. You can sample from an auxiliary distribution Q. Okay, and of course you need to choose the K such that the blue curve is above the red curve. Okay, so that's rejection sampling. I will skip this slide. There's some details about why it could have some issues in high dimensions and so on. Let's actually get to Gibbs sampling. Okay, so now we're going to talk about Gibbs sampling and Metropolis Hastings algorithm. These two are related to Markov chain Monte Carlo method, so that's where I want to spend the next majority of the time. Okay, so Gibbs sampling. Okay, so let's say I have a six-dimensional vector, six-dimensional random variable, random vector, and I generate samples. Okay, what are my samples? So it's x, x. Let me put superscript one, which is doesn't have to be R6, but whatever x1, x2, R6, and so on. Okay, x, n, R6. Okay, which is I just want six-dimensional realizations of this six-dimensional random variable. And the random variable is related to each other, and the random variables, each of the coordinates, they are related to each other in this way. Okay, this is a directed acyclic graph, right? Now, so you have this graph, you have the joint distribution between x1, x2, x3, x4, and x6, x5, and x6. Now you want to get samples from here. The way you do it is the idea of Gibbs sampling is to sample this sequence x superscript 1, x superscript 2 by updating one variable coordinate at a time. Okay, and I'm gonna kind of show what that means. In fact, let me just write it here. Okay, I want to get x1 to x6. I want to get samples which are x superscript 1, x superscript 2, x superscript whatever n, right? So the way I'm going to do it is let's call it x superscript 1, x superscript 2. Okay, this guy needs to have 6 numbers. This guy needs to have 6 numbers, right? The way you do it is start with some arbitrary numbers, maybe all zeros. Okay, for x first sample. Now the next sample you get by sampling from x1 given x2 is the previous number, let's say 0, x3 is the previous number 0, and so on. X6 is the previous number 0. Okay, this number you sample from this conditional distribution, which is one dimensional. Okay, and then this number you sample from another conditional probability distribution like this, which looks like p of x2 given x1 is, maybe this is let's say 3, x1 is 3, x3 is 0, all the way to x6 is 0. Okay, so you fill in the next number by sampling from here, where you assume the previous value is this. The previous values which are not in this row are from the previous row. Okay, so that's a dependence here, but that's it. That's Gibbs sampling. That's what that sentence says. Okay, sample sequence by updating one variable at a time. And another idea, well, so while doing the sampling, so if I want to sample, let's say, the fourth coordinate, okay, I want to sample the fourth coordinate. You fix all the other coordinates, right? X1 to x6. But the core idea is that how the graph is going to help us is that if the graph has these arrows going from top to bottom, then you just only need to condition on what is called the Markov blanket of this random variable. Okay, so Markov blanket is a more simpler concept than d-separation. Okay, all it means is that, oh, if I want to sample from x4, do I need the values of everybody else? You can see that, oh, if I tell you the graph, there is some conditional independences, so I probably won't need the values of x1 and x2. In fact, that's what's being told here. It's just saying that if I want to sample from x4, as long as you can tell me the values of the parents of x4, the children of x4, and the other parents of x4, other parents of x4's children, okay, then you can sample from x4 given only those guys. Okay, that's called a Markov blanket. Um, um, that's called a Markov blanket. Okay, and all it means is conditional independence. Okay, simpler conditional independence. It's just saying that I wanted to sample from x4 given everybody else, but I don't need everybody else. I just need the Markov blanket, which is parent, child, and child's other parents. Okay, parent, child, child's other parent. Yeah.
Even if we didn't have the graph going off of that sampling procedure, it would generate, let's say, 100
Yeah, if you didn't have this graph, you wouldn't have this efficiency. You would have, as long as you have access to these guys, you can.
Right.
Yeah.
So it wouldn't be, if we generate, let's say, 100 numbers, it would be dependent on all of them, but the last 10, 3, 4 numbers, right?
Oh, that dependence is
The
different.
market.
So you're talking about dependence across
Right.
these guys.
Yeah.
Oh, actually, these numbers, so these are six-dimensional vectors, okay? Here, Explore was talking about the fourth coordinate in the, let's say, the second example, for example. But you're talking about dependence here. This dependence is actually Markovian, in the sense that xn only depends on xn minus 1.
Right.
Xn minus 1 depends only on xn minus 2. Doesn't depend on other guys. Okay. I don't know. Yeah. Does this correspond to your idea of Gibbs sampling?
Yeah, I think I nailed it.
Okay. So here's, I mean, let's run through this example. So here's another graph. So by the way, the Markov blanket concept just means that, for example, if I want to sample a value from W, okay? If I want to sample from W and I have this graph, okay, this has too many nodes. So the way I would do it is sample from W given everybody else, right? Everybody else. Everybody else maybe took some values like f is equal to 1, p is equal to 1, c is equal to something, and I is equal to something. What you care about is that if I want to sample from here, I only need to know, as I said, parents. There are no parents for this guy. Children, there are 2 children. And these children don't have other parents. Okay, this guy doesn't have other parent, this guy doesn't have other parent. So you only care about, if you want to sample from W given everybody else, you only need sample of W given the children. Okay, the children took value 1 and 0 maybe in the previous round, then you just need this conditional probability. Okay, so that's efficiency. That's already efficiency that you're getting. Okay, and yeah, here we're just showing the how do you get this conditional probability. Okay, so this conditional probability of W is equal to something given 2 other values. You will have to yeah, you have to use Bayes rule to flip because what you have access to, if you had the graph, because it's a directed acyclic graph, you'll have tables like this, right? Because of the graph, in the graph, we had node given its parents, node given its parents. Those would be the factors, right? In the directors, in the factorization, and if those were the factors, you would have tables like that. Okay? Probability of W, probability of flu given W, probability of yeah. I don't know the last one. I think yeah, this should be C. Okay. All I'm saying is, if you had this subgraph, then you need to know some probability table for this. This is the table. Flu given cold weather, that's this table, and cold given cold weather, that's this table. You have only these tables, but you care about the conditional probability of W given flu and cold. So this requires some Bayes rule, right? Because you don't have this. You only have F given W, C given W, and W itself. So you have to do W given F and C is, you flip it, is proportional to F given W and C given W times probability of W. So that's just Bayes rule, okay? That's not a very important point. And here there's some computation going on. Let's kind of skip it. Yeah, ultimately you can compute those numbers. These are the numbers, and then sample from there. Okay, sample a W, you'll get some number, either 1 with probability 0.82 and 0 with probability 0.17. Okay. Any questions about that example? It was very quick. All I was trying to show you was that Gibbs sampling would have the conditioning on everybody else that just reduced to just children, parents, and children's other parents. And that, if you had the factorization of the DAG, okay, you will have to use Bayes rule to kind of compute that. Okay. I mean, you don't have to always, but it may be required. Okay. Now, here is a different graph. Here saying here we are trying to compute what is the probability of So how do we sample a new value for cold? Okay, now cold will have a very complicated Markov blanket because cold, has two children. The two children have other parents, and cold itself has one parent. Okay, so that's all of them together correspond to the Markov blanket. So probability of cold given everybody doesn't involve pollen, doesn't involve fever, doesn't involve itchy eyes. That's all I'm trying to say. So those three variables are not relevant. Everybody else is relevant. So as long as you can find the conditional probability of cold given those guys, cold present or not present, then you can sample from there. Okay. So that's the Markov blankets idea. This is the Markov blanket actually. As I said, you removed a few other random variables, and yeah, so doing that cold given the relevant Markov blanket variables requires some sort of usage of the tables, the factors, to figure out like what is the right factorization here. Okay. So yeah, so this is just a general expression for what we just saw. So there are parts which are not relevant. So except for the parents, children, and children's other parents, parts are not relevant, so they get cancelled. Okay, that's basically the summary of this slide. So finding the probability of xi given everybody else only depends on xi given its parents, and wait. Yeah, and the children of I. Okay. Anyway, don't worry about the general form here. It's not. It's just a generalization of what we just saw. There's nothing deep going on. So, what I want to switch to is some justification for Gibbs sampling. So we just saw, computational procedures, right? So why does Gibbs sampling work? And I think so this is where I think we'll understand a little bit about like what is Markov chain Monte Carlo doing. Okay, so for that, let me use this notes to say what a Markov chain is. We've already seen Markov chain because we saw Markov chains, Markov reward process, and Markov addition process. We also saw Markov chains when we were talking about hidden Markov models. Okay, so Markov chain is just a collection of random variables. Let's say x1 to xt, some number of random variables. And they are all related to each other through this condition, through this transition kernel, which is just the probability of x, let's say t plus 1 given xt. Okay, so they only like they're Markov because the new random variable only depends on the previous random variable and not all the random variables that are before that. Okay, so this is the conditional probability, the Markovian or the memoryless property. Okay, so Markov chain is just this, a sequence of random variables with a probability law like this. Okay, and the cool thing about Markov chains is that as long as few properties of the Markov chain hold, like ergodicity and irreducibility and a couple of, I think, one more property, then these a Markov chain will have what is called a stationary distribution. Okay, so let's say all these random variables, their support is the same. Okay, so each of the xi's is let's say two valued random variable, let's say binary valued random variable, then there's something called a stationary distribution. Okay, so if it's a binary valued random variable, remember that the p theta is just basically saying if I'm at 0, what's the probability that the next guy will be 0 or the next guy will be 1, and if I'm at 1, what's the probability the next guy is 0, next guy is 1. Okay, so this, for example, could be 0.2, 0.8, 0.8, 0.2, for example. Just a simple example. If I'm 0, I'm more likely to be 0. If I'm 1, if I'm 0, I'll switch to 1 with some small property. It's like if weather is hot, then it's going to rain. Not rain type of a example would be more appropriate. So this would be the P matrix actually. Okay, so transition probability matrix, and Markov chains have this. Some Markov chains have this nice property that there's existence of what is called a stationary distribution. Okay, it just means that if you keep generating new values, sampling new values. If you look at you start with, let's say, random variable x1 taking a value 0. Okay, then you figure out what's the sample next guy, because next guy will be most likely 0, but with some nice probability 1, and so on. Keep sampling, okay, and eventually you'll keep sampling zeros and ones in some order, right? I mean, that will be the samples. Now, if you look at the histogram of the values that these guys are taking, maybe you'll see a histogram of what's the probability with which variables are taking zeros, and what's the probability with which they're taking ones. Okay, you can draw a histogram, right? In the last 1,000 rounds, how many zeros happened, how many ones happened. Okay, given in this example they're only binary valued. Okay, so this distribution, okay, is called a stationary distribution in the sense that this distribution doesn't change. Okay, in the sense that if you go from that 1,000 to the next 1,000, it will be the same distribution of zeros and ones. Okay, so that's a property for some Markov chains. In general, the stationary distributions can be found by doing this computation. P is equal to pi. Okay, or actually pi transpose is 1 cross 2, 2 cross 2, 1 cross 2. Yeah. So solve this problem. Okay. So this is just a system of equations, right? It's let's call it pi1, pi2 times 0.8, 0.2, 0.2, 0.8 is pi1, pi2. Okay. So this distribution not changing is essentially saying that if you started from a particular distribution, so let's say xt has a probability of being 1 with some probability and 0 with some probability, apply this transition probability matrix, then the probability that xt plus 1 is 1 or 0 is the same as before. Okay? So there is a distribution, steady state distribution of what is the values that the new random variables are taking. Okay? So that you can solve for pi with this equation. Okay, so that's a Markov chain, and that's a stationary distribution. And the notion of all these Markov chain Monte Carlo sampling methods is the idea that the sampling methods will essentially capture some sort of a transition probability matrix that we saw. Okay, such that their transition probability matrices, there will be a corresponding stationary distribution for these transition probability matrices. Okay, these stationary distributions are going to be the distributions that we care about, in the sense the distributions from which we care about getting samples from. Okay, so let's say we care about getting a samples from a distribution P. Okay, now this distribution P is going to be the stationary distribution of some transition probability matrix or some transition probability kernel. Okay, as long as that guy is the stationary distribution of this transition probability kernel, then if I sample from the transition probability sequentially according to the Markov chain, I will be getting samples from this P. That's what I just said. That's the notion of stationary distribution, right? Now the question is, what is this transition probability kernel? Okay, Gibbs sampling provides one transition probability kernel. Metropolis Hastings provides some other transition probability kernel. You can think of those computational procedures as providing a way from going from one sample to the next sample, the Markovian property, such that if you keep sampling from this Gibbs sampling procedure again and again and again in a for loop, the samples that you're getting are from the stationary distribution that you care about, are from a stationary distribution, and the stationary distribution happens to be the distribution you care about. Okay. So why is this kernel related to the stationary distribution? And the stationary distribution is the distribution you care about, is because if you look at Gibbs sampling, if you had a target distribution P in mind, okay, like something like a target distribution P in mind, then Gibbs sampling involves P of xi given x1 to xi minus 1 and xi plus 1 to xp, let's say. If you had a distribution or random variable x. So this is the target distribution that we care about, from which we want samples. Gibbs sampling deals with some conditional probability distributions, but they are related to this guy. So as long as I'm sampling from this and I'm defining my transition probability kernel based on this guy's stationary distribution is that, because they are related. Okay? Because if I give you this, you can compute this guy. Okay, and based on the second guy, I created my transition probability procedure or kernel, okay, or matrix, And so of course it's gonna have, it could, most likely have this guy as a target, as the stationary distribution. That's the idea. Okay. So here, I mean, in this slide, I'm just showing that if you sample, like as long as you have a transition probability function or a kernel, like which goes from x to x prime, okay, and if this guy, so these kernels, most, for many Markov chains, this is a Markov chain, is going to have a stationary distribution which will have this property. This property is that pi of x prime is the, for every x prime, the probability of me sample, the probability of x prime taking a value whatever little x prime is that you were at x and you transition to x prime. Okay, it's like you were at x and you transition to x prime. Average or all the values from which you can transition to x prime. Okay, so if you look at this, it's saying that the probability of x taking a value 1 is you were at 1 and you transition to 1, which is the probability 0.8, or you were at, I guess, 0 and you multiplied with 0.2. Okay, so this times this times this is that, right? Like that's just matrix multiplication, matrix linear equation. So that's what's written here. Okay, so starting from any state, any value, you transition to x prime, average over that. That's going to be the probability of x prime. Okay, this is the same stationary distribution. Okay, so the question is, given p, which we care about, from which we want to sample, we want to find a this transition probability kernel or transition probability function such that the stationary distribution is p itself. So what the input is p. I want to find this transition probability matrix such that p is the stationary distribution. As long as I can do that, then I can sample in a Markovian way from this transition probability distribution, and those samples will resemble as if they're coming from p. Okay, that's the core idea. And okay, I'm just telling you what the okay, so there's actually a small proof, so I'm wondering if I should do that. Okay, I think I will skip that, but it was an explanation of why Gibbs sampling's choice would give you a stationary distribution, which is the target distribution. Okay, and that requires just checking what is called a detailed balance equation. Okay, so we don't need to know the details now. But Gibbs sampling, what does it work on? It works on conditional probabilities, right? One-dimensional conditional probabilities. Those sequence of one-dimensional conditional probabilities that Gibbs sampling works on categorize this Q function or this Q transition probability matrix, and that transition probabilities matrix to define what the stationary distribution is. That to check that guy has a stationary distribution with some pi, you just see whether that pi and that transition probability matrix satisfy what is called a detailed balance equation, which is this equation. This equation here, and you can show that p of x, our target distribution, and the Gibbs sampling kernel or this transition probability matrix satisfy this equation. Okay, as long as it satisfies this equation, you can say that the Gibbs sampling guy does have p of x as the stationary distribution. Okay, this is just a verification. This is a way to say, oh, if this equation is true, then pi is a stationary distribution for this guy. Okay, and we can check this condition for Gibbs sampling. And we do that in the next slide, but I will skip that here. Okay, so let me do that animation before we run out of time. So yeah. Okay, so let me pause it. Okay, so what are we trying to do? This is our some two-dimensional probability density function which has higher mass here. So the higher mass is like this is like the peak of the hill, okay, of the distribution. It's a very messy distribution. Okay, it's like curvy, right? Now, how do we sample? So let's actually, yeah. the way you're gonna sample. So here, so what is this picture showing? So forget about that. Lot of options there. We care about sampling from here, okay? And here below we are showing bunch of samples that have already been collected. So don't worry about that. Those are some marginal distributions, okay? So let's say. uh, Yeah. So let's say we are at some point here. Okay, so we are doing only two-dimensional sampling. Instead of x1 to x6, we have just x1, x2, two coordinates. Okay. So we are at some x1, x2 value, previous value. Okay. So we are saying to sample the next guy, okay, get the next two-dimensional vector. Okay. We're gonna keep one of the coordinates constant. So let's say x1. So let's say this is x1, x-axis is x1, and y-axis is x2, and there was some previous value. We're going to keep x2 the same and sample a new value of x1. Okay. That's this guy. Sorry, we'll keep the x2 value the same, which is this constant line here. Okay, and sample a new x1 that pushes to new x1 to somewhere over here. Okay, and now fix that x1, which is this vertical line, and sample a new x2, and this happens to be over here. Okay. That's what was happening in game sampling, right? So just to understand, this was the previous sample. We're gonna do two steps because we want to create a two-dimensional new sample, right? We're gonna do it in two steps. One is keep x2 the same and sample a new x1 that's going horizontally because x1 is on the horizontal line. And then once we sample new x1, sample a new x2. Okay, so fixing that x1. Okay, so that gave us this new point. Okay, so we went from a previous sample, let's say x10th example, 10th observation, 10th sample, to the 11th sample. Okay, that's the green arrow, but we do it in two steps. Okay, coordinate wise. And in higher dimensions, we do it again coordinate wise. You know, if there are p dimensional vectors, then we have to do p steps like this, keeping everything else constant, sampling the jth coordinate, j+1 coordinate, and so on. You can keep a fixed order if you want. Yeah, it's fine. Keep fixed order is fine. You don't have to change the order. I mean, if you change the order, it should not affect anything. But keeping a fixed order is fine. Yeah. Actually, changing the order, I should think about it a little bit. Because it's not, so here you cannot change the order, right? You have to keep one of them. So if you're going from x1, x2 to, one example, another example, you have to keep one of the coordinates fixed. The question is which coordinate you will keep fixed. You can actually change, You can change, yeah. So that's skip sampling. And we have pretty much run out of time. So there's another thing about the Markov chain Monte Carlo techniques because we are sampling, right? And also their samples are dependent; they are not independent. So x10th observation has something to do with the 9th observation. We just saw that, right? So this dependence is something that you need to be aware of. Like you get a bunch of samples; they are all related to each other. There's also this another issue of this Markov chain. You want to get samples from a stationary distribution. Okay, to get to the stationary distribution, you need to do an initial what is called a burn-in period, where you have to kind of run the Markov chain for initial 1,000 rounds or 10,000 rounds or something like that, and hope that after those 10,000 number of samples, which you can discard, now the Markov chain is in steady state, and therefore you're getting samples from the stationary distribution. Okay, so that is something that's operational that you need to do. So you need to what is called a burn-in or burn-in period that you need to spend time on. What did you say?
The kernel or transition matrix.
Yeah.
Some sort of initialization to do?
No, I just this is what this is what you would do. You start with some random sample. As long as you have access to these guys, you can keep sampling, right? New ones. So there's no, in the sense, all I'm saying is there's a burn-in, which means that you finish like 10,000 rows here and hope that after 10,000 rows, you are actually getting samples from the stationary distribution.
I think all I was asking like in this station is kind of initialize everything to 0.
Yeah, you can start with anything here.
Chugging through, moving the line around.
Yeah, I started. So this was a 6-dimensional example. So this is a 6-dimensional thing. Now you have to keep one thing constant, not one thing, sorry, everything else, 5 other guys constant, and move 1 coordinate at a time. So that's what we are doing, right? So we are keeping x2 to x6 constant and sampling the new guy that happened to be 3. Now we keep 3 and everything else constant and sample the next guy. Maybe it's 1. Okay. And so we keep 3 and 1 constant and these 3 zeros constant and get some new number.
So in this case, you could think of the burden if you just had x1 and x2, you didn't have all the rest. And
Yeah.
Going back to that example you were showing,
Yeah.
we be at the origin, we started sampling and move up till we got into the range from that.
Yeah, so Berlin is about this direction, number of observations. But yeah, if you did not have this part, yeah, what we showed in that illustration was keeping one guy constant, getting the next number, and then keeping that number constant, getting the next number. That's what we were doing. So that picture is the same as this picture, like keeping one coordinate constant, going to another number, keeping that guy constant, going to another number. So we need these conditional probabilities. Okay, we need these one-dimensional conditional probabilities. So we are sampling from these one-dimensional conditional probabilities in a sequence. So we will have 6 such one-dimensional conditional probabilities. For each row, we need to get 6 one-dimensional samples, and then for the next row again 6 one-dimensional samples, and so on. Okay. So this 6 one-dimensional samples is the Q, the transition probability matrix. It's not really a matrix here. You can see that there are 6 individual samplings going on, but together they constitute the Q, whose stationary distribution is the target distribution P. That's what Q Gibbs sampling tells you. This is the Q. So Gibbs sampling is just a one initialization of Markov chain Monte Carlo technique where they specified what the Q is. The Q is, if you know the P, Q is going to be just the marginals. I mean this one-dimensional conditional probabilities given the P. Okay. If this is the Q for Gibbs sampling, so different Markov chain Monte Carlo techniques will have different Qs. Okay, different such guys. Okay.
And that Q is how you arrive at this transition matrix, more or less. Strategy of how you build it.
Yeah, so they built it. So the people who invented Gibbs sampling, they built this Q. This 6 guys together is a Q whose stationary distribution is the target distribution we want to sample from. Okay. Metropolis Hastings is another technique where there's a different Q whose stationary distribution is also the same P. Okay, the same distribution we want to sample from, and so on. Okay. So we've run out of time. So if the questions, just come forward. Otherwise, we'll talk next time more about learning. Okay, we'll do learning next time.
Actually, you did have a question about our project.
Okay, 1 second.
Sure.